Hi, guys. Okay, so let's look at the chapter 8 problems from the Libre textbook by Tro. And this chapter is the quantities and chemical reactions. And we're going to look at the exercise problems within the text, within the chapter in every section. So the first set of exercise problems is 8.2.1. Here, we are given a chemical reaction and we're being asked to find the formula units. In other words, we have the old term molecules, how many molecules are reacting on each side, the reactants and the products, and a more modern term is the moles, how many moles are on each side, the reactants and the products. So here we see, you can say that we have one molecule, or this is the formula unit, one molecule of potassium bromate, okay, and this also means 1 mole of potassium bromate is reacting with 6 molecules of potassium iodide, okay, and that also means 6 moles of potassium iodide to give you, oh, and also 6 moles of is also reacting with 6 molecules of HBr, okay, and this also means 6 moles of HBr. So these are the reactants. So I'm going to just put this here, HBr, and this is potassium iodide, and this is KBrO3. So these guys are the reactants. And I'm going to, in short, I use them as R. Okay, to give you 7 molecules, and this also means 7 moles of potassium bromide, KBr, okay, so KBr, and 3 molecules of H2O, and this also means 3 moles of H2O. And these guys are the products to give, this is the product, and product, I use it as this in short. Okay, so this is this very simple. So formula units is basically the number of molecules. All right, next is you are given a reaction, right? And this is a combustion reaction in which they are combusting pentane, C5H12. Okay, C5H12, this is the name of this organic compound, and they are saying, given you the moles and find the moles of water. So here is something you have to understand is the mole to mole ratio. Anytime you're given a reaction, okay, we look at the mole to mole ratio, the moles of one and the moles of another. So here we will see the mole to mole ratio is basically 1 mole of C5H12 is basically producing 6 moles of H2O, right? So this means 1 mole of, depending what we are trying to convert to and from, we can create 2 conversion factors. So basically this is the equality. 1 mole is equal to 1 mole of A is equal to whatever moles of B. So that thing. So 1 mole of C5H12 and 6 moles of water is 1. And then the other is 6 moles of water and over 1 mole of C5H12. Okay, so these are the 2 equalities, and these are the mole fractions, mole to mole, the units, the mole to mole fractions, okay, or molar ratios. Okay, so, and let me make this also small. All of this should be small size. All right, here. So this is thing. Now we are going to write down what is given to us. Same story. Write down the given. You are given 0.6, sorry, 0.0, okay, 0.0652 moles of which one? C5H12, and we want to convert these moles to the moles of water. So in the moles, there's 6 moles of water is going to be on the top. So we're going to use this conversion factor, which cancels out the moles of C5H12. And only 1 mole of C5H12 is, that's the relationship. So we are going to use this conversion factor in which the moles of water is on the top or is in the numerator, so that the moles of C5H12 cancel out. Okay, so what is left now? So what is left is 0.0652 times 6. Divide that by 1. And this gives you 0.0652 times 6 is equal to 0.391. 0.391 moles of water. Always, it's very important. You write down the entity that is in question, the entity that is you are trying to find, the answer, the units, all those things. Okay, so that is the answer. All right, next is we're going to look at the next one. You are given a reaction in which aluminum chloride is reacting with water and it's giving you aluminum oxide and HCl. So here we are trying to find the moles of HCl when you are given the grams of water. So moles of Al2O3 aluminum oxide we're going to find, and we're given the grams of water. Okay, so what are we going to do here? We are going to see, this is a strategy that they follow. You take the grams of entity. If you want to find, take A, whatever, one entity and the other entity that you find. So A is given to you, okay, and you're trying to find whatever. Either you're trying to find the moles of B or you're trying to find the grams of B, doesn't matter. So you're going to still use this strategy. So write this down. Strategy is you're going to take the grams of A, let's say grams of A, and you're going to convert that to moles of A. So how will you do that? Moles of A, how are you going to do that? You are going to take the grams of A, convert to moles of A using the molar mass of A, molar mass of A, okay? And that converts to the moles of A, okay? Next is, that gives you the moles of A. Next, you're going to convert that to the moles of B, and here would be the, so how will you do that? Moles of B, you are going to use the mole to mole ratio, okay? So you will use the mole, so let me use this color, mole to mole ratio of between A and B. Mole to mole ratio. This mole to mole ratio creates the conversion factors, right? And then you have, next thing is the moles of B, convert that to the grams of B. And how are you going to do that? You're going to use that, the molar mass. Use the molar mass of B. Molar mass of B, and that gives you the grams of B. Okay, so this is the strategy. All right. So let me just clear this up. 23.9 grams. 23.9 grams of water. Okay, so that's your strategy. And in this strategy, you will now, certain things are not given to you, obviously, in the question, that is the molar masses. But we are expecting you, if you understand these, that's the whole thing with the reaction stoichiometry. So if you understand these, you are going to, so I'm going to erase this one. I don't need this. So if you understand the reaction stoichiometry, you would understand that the finding the molar mass and, balancing the equation and making sure that, these are the coefficients, these are the moles that are going to be used in doing the molar mass. So this is important. So that if this one is not balanced correctly, if these coefficients are not correct, you're not going to get the mole to mole ratio correct, right? If you don't know how to write the formula correctly, you are not going to, you need the formula, right? The formula of the compounds. And if these formulas are not done correctly, you don't know how to write the formula, then you can't get the right molar mass. So it's more getting complex. But other than that, if you're able to do the rest of the stuff, then it's easy. So let's find the molar mass of two entities. So we are just looking at water and we are looking at Al2O. H2O3. But wait a minute. In this question, since the question is only asking for the moles here, so we do not need the molar mass of Al2O3. We are okay. So just use the water. So 2 moles of water. But yeah, that's the relationship between the two, water and Al2O3. That's the only 2 things to focus on. So there are 2 hydrogens. There's 1 oxygen. Hydrogen is 1 and then oxygen is 16. So here you get 2 plus 16 is equal to 18 grams per mole. Okay. So now let's write down what is given to us. 23.9 grams of H2O is given. First, convert that to moles times 1 mole of, sorry, just make this here. Okay, once again, 23.9 grams of H2O times 1 mole of H2O over 18 grams of H2O. Multiply by mole to mole ratio. Mole to mole ratio is what? It is 3:1. So 1 mole of Al2O3 goes on the top because that's what we need to find. We need to cancel out the moles of H2O, right? The question is asking us find the moles for Al2O3. That is why these are going to go on the top. So let's put this here. So this moles of Al2O3, moles of Al2, that's what we need to find. So they go on the top, but this grams of water and the grams of water cancel out. This is grams, 18 grams of water cancel out. Okay, moles of water, and once again, the moles of water cancel out. Okay, so this is all dimensional analysis. So now you are left with 23.9 times 1 times 1 divide by 18 times 1. Okay, so let's do this. What do we get here? 23.9 divided by 18. So that is 1.32. Wait a minute. 3. Oh, wait, sorry. I made a mistake here. Sorry about that. Okay, so it's not 1 mole. It's actually 3 moles. Sorry about that. 3 moles of water. Okay. So discard the previous what I said. So 3 moles of water. So this is going to be 18 times 3. 18 times 3. So now, okay. 18 times 3 is 54. So 23.9 divided by 54. 23.9 divided by 54 gives you 0.442 moles of Al2O3. Very important in reaction stoichiometry to write down which entity is in question. Remember, so many are there. So this is the answer. Okay, so this is how you will set up the problems where the grams is given and you just need to find the moles. So this is the moles that you need to find. So that's why you didn't do the last step, but you stop here. This is where you stop. So in this case, you can stop here because that will just give you the moles. Okay, next is the grams. So same strategy. Let me copy this again. So you have it all in one place. Okay. All right, so here we are, the same strategy we are using. And the same strategy is basically this thing here. Sorry. Okay, so this is what we are given the grams. In this case, we are given the grams, and the grams is given of methane, CH4, and we are being asked to find the grams of HCl. Okay, so these 2 entities are in question. So we are going to now find the molar mass of molar mass of CH4 and of HCl. So CH4 is 1 carbon and 4 hydrogens. Carbon is 12 and hydrogen is 1. So 12 and then 4, and this gives you 16 grams per mole. So that's for CH4. For HCl is 1 hydrogen and 1 chlorine times hydrogen is 1, chlorine is 35. So this becomes 1 plus 35 is equal to 36 grams per mole. Okay, so this is the molar mass of the two entities that are in question. Because the question is starting with grams, and you are being asked to convert to grams of one, and you're being asked to convert to the grams of the other. So 9.7 grams. Okay, so grams of the other, that's why you do this. So here. All right, so let's write this down. We are given 100 grams of 100.0 grams of what? CH4. Okay, so first convert it into moles, and we'll just do all in one step. So 1 mole of CH4, you can break it up also, that's fine, over, and this is 16 grams of CH4. Okay, so 16 grams of CH4, and this, and then mole to mole ratio. It's very important that the reaction is balanced. So we see 1 mole of CH4, 1 mole of CH4 is giving you 4 moles of HCl, 4 moles of HCl, 4 moles of HCl. And then next is because the question is asking grams of HCl. So 1 mole of HCl gives you how many grams? 36 grams of HCl. Okay, so this is the setup. Now here you see that, let's cancel out the units. Grams of CH4, grams of CH4 cancel out. Moles of CH4, moles of CH4 cancel out. Moles of HCl and the moles of HCl cancel out. And now you're just left with 100.0 times 1 times 4 times 36, divide by 16 times 1 times 4. 16 times 1 times 1. Okay, so let's do the math. So here we have 100 times 1 times 4 times 36, and that gives you 14400. Divide that by 16. Divide that by 16, and that gives you 900. 900. So I'm getting 900. Okay, so what I'm thinking is they used, again, the book has used 900 grams of HCl. The book has used consistently, I have noticed that the book has used the exact number of the exact numbers from the periodic table. So the book has used the same number of molar mass from periodic table, whereas I have rounded off the mass. Okay, so that's why there's a slight discrepancy in the answer, but nonetheless, this is the procedure. Okay, so that will give you the right answer. All right, so that's the answer, grams of HCl. Okay, let's look at again next question, which is about, you are given, in this case, we need to find the limiting reactant. Okay, limiting reactant. Now, limiting reactant, if you understand, is the one that gives you the less product, the lesser of the product. And next question is, how much of the other product that remained unused was like leftover? So how do we calculate that? Now, in this case, the strategy is still the same. This strategy, this is still the same strategy you're going to use. So I'm going to bring this up here. And let's see, copy, and here. All right, so the strategy is still the same. Oh, Okay, so here we are looking at the only difference we are going to look at is the compare the reactants. So compare two reactants. Okay, so compare two reactants with the products. Okay, so compare to, what am I doing here? Compare reactant 1 and reactant 2. How much of the product is this one going to give? How much of the product is this one going to give? The one that gives you the lesser of the product, that is the limiting reactant. Okay, so you know the limiting reactant is limiting, L-I-M-I-T-I-N-G, limiting reactant, R-E-A-C-T-A-N-T. Okay, now, so we are going to compare. Once again, in this case, we are looking at two things. We are looking at the magnesium oxide and we're looking at H2S, and we're going to find out how much of the magnesium sulfide or water can you produce, but I'm going to do magnesium sulfide. Okay, so magnesium oxide. If you, so we are comparing the two, but using the same strategy. So first is magnesium oxide. Okay, magnesium oxide, using the magnesium oxide, how much of the magnesium sulfide can you produce? Okay, on the side, we would need the molar masses. So let's do that on the side, first of all. Molar masses, let's put it in a different color. Molar mass. Okay, magnesium. So we are comparing magnesium oxide and magnesium sulfide. So here we have one magnesium. Magnesium is 24, and we have one oxygen. Oxygen is 16. So here we have 24 plus 16, and that gives you 10, 2, 4, 5, 2, 3, 4, sorry, 40 grams per mole. So that is the magnesium oxide. Next is the magnesium sulfide, MgS. Magnesium sulfide is again one magnesium, okay, times 24, and that is 24 grams. And then you have one sulfur, and each sulfur is 32. So this is 32 grams. So 4 plus 2, 6, and 5, 56 grams per mole. This is the magnesium sulfide. And the next is we are comparing H2S. So H2S, here in H2S, there are two hydrogens. Each is one, right? Each is one. So this is 2 grams. And sulfur, one sulfur, and sulfur is 32. So this is 32 grams. So a total is, so these are basically grams, 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 grams. Okay. I don't know if Sally, am I writing here? Oh dear, 24 grams, 16 grams. Okay. And then same as the case, this one is grams, grams. Okay. And then this becomes 34 grams per mole. Okay. Now we have okay. All right. Now we have all these molar masses we have on one side, which is a good thing. Now we are going to just put them on a side and we're going to just apply them. Okay. We will just apply these in the scheme. So here. Oh no. What's happening here? Give me 1 minute, please. It's about getting some space here, so thank you. All right, now let's do this. So compare, first of all, magnesium oxide to magnesium sulfide. Magnesium oxide to magnesium sulfide, like how much of it can we get? So when we use 22.7 grams of magnesium oxide, first step is what? Converted to grams to moles. Okay, so here we have 1 mole of magnesium oxide, 1 mole of magnesium oxide, and that is equal to, we calculated the molar mass, and the molar mass of magnesium oxide was 40. We calculated it as 40 grams of magnesium oxide. The next step is mole to mole ratio. So it's 1 to 1. 1 mole of magnesium sulfide is produced when 1 mole of magnesium oxide reacts. Next is, we can stop here, but we will continue. I like to do it in grams. So 1 mole of magnesium sulfide is equal to how many? 56 grams. Okay, 56 grams of magnesium sulfide. So this way, when you set up the problem, you're going to cancel out the grams of magnesium oxide, moles of magnesium oxide, 1 mole of magnesium oxide. So that was moles, just for the sake of space, I did that, but that's mole to mole ratio. Okay, so this is going to now give you the 22.7 times 1 times 1 times 56. Divide that by 40 times 1 times 1. What do you get here? Okay. So let's do this. 22.7 times 1 times 1 times 56. And this gives you 1271.2. Divide this by 40. Divide by 40. And that is 31.78 grams of magnesium sulfide is produced when 22.8 grams of magnesium is used. Let's look at the other one. Okay, so we are given, the next is 17.9 H2S. So H2S is, next is using the H2S. And how much of the magnesium sulfide is this producing? So H2S is what? H2S is 17.9. 17.9 grams of H2S. Okay. Times moles, 1 mole of H2S over the amount. So H2S is 34 grams of H2S. Okay, times mole to mole ratio. H2S is 1:1. Yeah, 1 mole of H2S is giving you 1 mole of magnesium oxide. Okay, and that gives you, magnesium sulfide. Magnesium sulfide. This is magnesium sulfide times 56 grams of magnesium sulfide, 56 grams of magnesium sulfide over 1 mole of magnesium sulfide. Okay, 1 mole of magnesium sulfide. So what do you see here? You're going to cancel out the grams of H2S, and the grams of H2S cancel out. Moles of H2S cancel. Moles of magnesium sulfide cancel. Okay, so what do you get here now? You have 17.9 times 1 times 1 times 56. Divide that by 34 times 1 times 1. Okay, so what do you get? Okay, here we see 17.9 times 56, and that is 1002.4. Divide by 34, and that is 1002.4 divide by 34, and that gives you 29. This gives you 29.48 grams of magnesium sulfide. So you see here, which one is giving you less? So when you used 17.9 grams of H2S, you were able to produce 29.48 grams of magnesium sulfide. So the one that gives you less is the one that is acting as a limiting reactant. Okay, reactant or reagent or whatever, because you're able to get less. Okay, so that is right. But now the question is, how much of the magnesium oxide is left over? So how are you going to do that? So it's a space issue here. So give me 1 minute. I'm going to condense this, make it small, and we will have some space then. All right. Okay. So this is the answer here. Now we are going to look at which one is going to be how much of the magnesium oxide is left over. So in other words, now we have to go, this is looking backwards. Now going backward, in order to produce, so we clearly know that all of the H2S that you use, all of the H2S that you're using, all that H2S is going to be used up, right? Because then it just maximum you can get is 29.4 grams of magnesium oxide. But leftover magnesium sulfide is going to 29.48 grams of magnesium sulfide will be produced. But the question is now excess. So in other words, in order to produce 29.48 grams of magnesium sulfide, how much of magnesium oxide is being used? So this is the question you will be asking. So let me write this down. In order to produce 29.48 grams of magnesium sulfide, how many grams of magnesium oxide will be used? Okay, so we know the excess is in excess, but how much is going to be used? Only then you can find out the leftover. Okay, so here. Okay, so this is what we are trying to address now, the last part. Okay, so we want 29.48 grams of magnesium. So here we are looking at the relationship of magnesium sulfide to magnesium oxide. Okay, so this is the relationship. So write it down. 29.48 grams of magnesium sulfide. Okay, 29.48 grams of magnesium sulfide times 1 mole, same thing, same strategy, 1 mole of magnesium sulfide. Okay, 1 mole of magnesium sulfide is 56 grams. That's the molar mass of magnesium sulfide. Same thing, you're going to convert it into mole to mole ratio. So we see that magnesium sulfide and magnesium oxide are 1:1. So 1 mole of magnesium sulfide and 1 mole of magnesium oxide. Okay, you put them in the mole to mole ratio. Next, convert that to, you can actually leave things only at the molar level also, just moles and moles if you're just comparing mole to mole, but I like to do it in grams. So 1 mole of magnesium oxide is 40. 1 mole of magnesium oxide is 40 grams of magnesium oxide. Okay, so here you will see that the grams of magnesium sulfide cancel out. Moles of magnesium sulfide and the moles of magnesium sulfide cancel out. Moles of magnesium oxide and the moles of magnesium oxide cancel out. So you are just left with the moles of no, you're just left with 29.4 times 1 times 1 times 40, the grams of magnesium oxide, over 56 times 1 times 1. So let's do this. Here you have 29.4 times 40 divided by 56, and that is 21. That is 21.05. grams of magnesium oxide will be used. Will be used. But how much is left then? Then the total was how much? The total was magnesium oxide was 22.7. So again, let me make this small. Sorry. Okay. So here, small, right here. Okay. So now we have will be used. So the total was how much? The total given was 22.7. Okay. 22.7. Total was 22.7 grams minus the one that is going to be used is 1.05 grams. Okay. 1.05 grams. So what is left? So 22.7. So let's make this 22.70. So here we have 22.70 minus 21.05, and you get 1.65. 1.65 grams is left. And which is this? Magnesium oxide. Okay, so that is the answer. This is the leftover. Okay, this is the answer to this thing. So you will be, asked, or this is actually a test question. Okay, this is the test question, but not the leftover, but at least find the limiting reactant, at least the limiting reactant and the percentage yields. Okay, these are all important things. Okay, so that's one piece. Okay. All right, so yeah, your answer here is 1.5, but I'm getting 1.65. So again, it's like, something. Okay, now the last is the percentage yield. Okay, so you are given carbon tetrachloride. It's reacting with 2 moles of, no, it's reacting with excess of hydrogen fluoride, right? It's balanced as 2 moles, and it's giving you Freon and HCl. So the question is, what is the percentage yield? So keep this in mind that if it is given, this is the actual. Okay, this is the actual. This is always the actual. The question may say actual, but the question, if the theoretical yield, they haven't specifically mentioned the theoretical yield, then it definitely means this is the actual yield. Okay, this is so you need to find. So the formula is percentage yield is equal to actual yield, actual amount in grams over the theoretical. Okay, theoretical times 100%, times 100%. Okay, so in this case, you are given 2 things. One is the carbon tetrachloride. Okay, and you are comparing it with CF2Cl2. Like if you are using 32.9 grams of carbon tetrachloride, how much of the CF2Cl2 will you produce? This is the, in theory, theoretical yield. Okay, always keep in mind that the actual yield is, actual means in reality. So this is actually yield. This is the real reality. This is depends on the productivity in the lab. But theoretical is in theory, in paper, right? It's on paper. So on paper only. So on paper, when you do the theoretical yield, the reality, is coming after chemical reactions, in your hand, but when you get it depends on, what your productivity is. Okay, next is, so how do you do? You're going to first calculate the theoretical yield. We don't have the theoretical yield, so first calculate the theoretical yield always. Theoretical yield. Okay, so we are given, so for that, we are going to calculate the molar masses. So molar mass, because we need that information on the side. So molar mass of CCl4 is, there is 1 carbon, there are 4 chlorines, One carbon is 12 grams and 4 chlorines are 35. So what do we have here? 35 times 4 is equal to 140 plus 12 is equal to plus 12 is equal to 152. 152 grams per mole. Okay, so this is one piece. And then the rest is CF2Cl2. So there's one carbon, there are 2 fluorines, and there is 2 chlorines. Okay, so the weight of one carbon is 12, the weight of 2 chlorines is 35, and the weight of fluorine, as far as I remember, is 19. Okay, so here we get 19. So 12, 19 twos are 38, and then 35 times 2 is 70. So here you add these guys, 70 plus 38 plus 12, and you get what? 120. 120 grams per mole. All right. So these are the molar masses. Put them on one side. The same scheme that is going to be followed even for the theoretical yield. It's the same story. Okay. Mole. Okay. So okay. Same, I'm going to just bring in the same scheme. Okay, and then just bring the same scheme. Okay. Copy. All right. So same thing here. Okay. Other things also get carried. Okay. So we have now the same scheme. So what are we doing now? What is the percentage yield? So carbon tetrachloride, 32.9. So let's see how much of the freon can you produce from this. So 32.9. So 32.9 grams of CCl4. Okay, convert that to moles. So 1 mole of CCl4 over the weight is 152 grams of CCl4 times now the mole to mole ratio. So this one is 1:1 only. Yeah. So 1 mole of CF2Cl2 is being produced when 1 mole of carbon tetrachloride is reacting, and that gives you 1 mole of CF2Cl2 here, and it is 120 grams. Oh, sorry. Yeah, 120 grams of CF2. That's the molar mass of CF2Cl2. Okay. So here you will see, you will cancel out the carbon tetrachloride grams, moles of carbon tetrachloride cancel out, the moles of CF2Cl2 cancel out, and you are just left with the grams of CF2Cl2. So let's see what we get here. 32.9 times 1 times 1 times 120. Divide this by 152 times 1 times 1. Okay, so what do you get here? 32.9 times 120 divide by 152, and that gives you 25.97. 25.97 grams of CF2Cl2. Okay, that is the theoretical yield. In theory, we produce that, but the actual is, this is in theory. So let me put this here. This is theoretical. Amount or theoretical yield. Yield is the amount. Okay. Next is you just do the percentage yield. Percentage yield is equal to the actual over the theoretical, and the actual is 12.5, 12.5 grams, okay, over the theoretical is 25.97 times, this is grams, times 100%. So what do you get here? 12.5. So 12.5, divide that by 25.97 times 100%, and you get 48.13. 48.13% yield. That is the answer. Okay, so that is your percentage yield, which is always, keep this in mind, that the actual amount is always going to be lower than theoretical because there's going to be some productivity loss. Okay, some productivity loss will be there, which is going to create like you will lose the product. So actual amount less than theoretical. All right. Okay, so that is your 8.6.1, that's a percentage yield. And then the last one, although they haven't given any question for this one, but I'm still going to do it because this relates to the enthalpy change, whether the reaction was endothermic or exothermic. So here, two types of reactions, as you know, for this endothermic, and exothermic. So exothermic reactions will release heat. Exothermic reactions and endothermic reactions. So here they are going to they take heat or they absorb heat. They take heat, and exo, they give heat. They give heat. Okay. Endo is when they take heat, they are basically like the heat is, so when they take heat, the value of delta H is a positive number, is plus sign. And when they give heat, the value of delta H is negative. Okay, the enthalpy change, it's the heat of a reaction. So let's see, take heat, delta H is a positive number, and give heat, delta H is a negative number. Okay, in endothermic, the heat is a part of a product. Endothermic, yeah, but in exothermic, the heat is a part of a reactant. So in this case, the heat, this seems like this is an exothermic reaction because the heat is a, so let me write this down. Another note, please note that heat is measured in kilojoules. Okay, that's the unit. Is a part of products. Okay, in exothermic reactions. And in endothermic reactions, the heat is a part of a reactant. Okay, reactant in endothermic reactions. So the rest of it is just, you know, simple math. Reactions. Okay, now let's do this. Sorry. All right, here we have a scenario where they're asking you to find how much is the heat released when 58 grams of sulfur dioxide reacts in excess. So once again, you are going to look at in this case, it's simple. You're going to take the mole to mole ratio with the heat. Okay, so 2 moles of sulfur dioxide, okay, are producing 198 kilojoules of heat. Okay, so the moles of mole to mole ratio is 2 moles of sulfur dioxide over 198 kilojoules of heat, or 198 kilojoules of heat over 2 moles of sulfur dioxide. And the rest is same. You take the grams of sulfur dioxide, convert that to moles of sulfur dioxide, and then use the mole-to-mole ratio of the heat to find out how much of the heat is produced when you use a certain grams of a starting material. Okay, so let's do this. So in this case, once again, we would need the molar mass of sulfur dioxide. So molar mass of sulfur dioxide. So how are you going to get that? Molar mass of sulfur dioxide: 1 sulfur, 2 oxygens. Each sulfur is 32 grams. 1 sulfur is 32 grams. Oxygen is 16 grams. So here you have 32, 16 twos are, so this is 32. So this becomes 64 grams per mole. So all you need to do now is you're going to write down the 58 grams of sulfur dioxide times 1 mole of sulfur dioxide over 1 mole of sulfur dioxide over 64 grams of sulfur dioxide. Multiply that by the mole-to-mole ratio. So how many it is? It is 2 moles of sulfur dioxide, 2 moles of sulfur dioxide in the reaction. So I don't have to write this when we write this here. So 2 moles of sulfur dioxide are producing 198 kilojoules of heat. Okay, so now you just cancel out the grams of sulfur dioxide. Grams of sulfur dioxide cancel out. Moles of sulfur dioxide cancel out. And you're just left with 58 times 1 times 198 divided by 64 times 2. So what do you get here? $58 times 1 times 198 is equal to 11,484. Okay, divide that by 64 times 2. 64 times 2 is equal to 128. So here you have 58 times 1 times 198. 198 is equal to, okay, divide by 128 and you get 89.71 is equal to 89.71 kilojoules of heat. And that is the answer. And this is the value of delta H is equal to positive 89.71 kilojoules. Okay, so that is the answer. So that's the way to do the enthalpy questions. Okay, so just treat them like the reactants and the products and you won't go wrong. And that's it for this chapter. Okay. I'm just trying to make this small. It's not doing, okay. Anyway, so this is the all right. Thank you for watching. Bye-bye.